Welcome to your first lesson of the Biomechanics of Human Movement for OCCT 2000. In this lesson, we're going to be going over the concepts of motion, levers, and the center of gravity and the base of support. First, to understand motion, we need to understand what is force. Force is not something tangible. It's a concept. It's an influence that changes the state of rest or motion of an object. Force, as you'll remember from physics, is a vector quantity represented in magnitude, direction, and the point of application. The magnitude is represented by the length of the arrow. The direction of the force is the direction of the arrow. The equation of force is encapsulated in Newton's second law, which we'll mention now, but the equation stands as force equals mass times acceleration. Mass being the quantity of matter that makes up a body or an object, measured in kilograms, and acceleration measured in meters per second squared. The unit of force is Newton. That brings me to the next important concept in motion, which are Newton's laws of motion. The first one is the law of inertia, which means that every object continues in a state of rest or motion in a straight line except when an external force changes its state. For example, consider the soccer ball. This soccer ball is at rest and will remain at rest unless an external force, like a foot, changes its state of motion. Newton's second law is the law of acceleration, which is when a force is applied to an object, it will move in the direction the force was applied, and, depending on the size of the force and the size of the object will accelerate accordingly. Again, back to the soccer ball. The bigger the kick, or the greater the force, the further the ball is going to move. Similarly, if the mass of the ball was greater, it wouldn't move as far. Newton's third law is the law of action and reaction. To every action, there is an equal and opposite reaction. If an athlete exerts a force onto the ground in order to push off, the ground will exert an equal and opposite force on the athlete, pushing them up in the air. The first force of the athlete pushing into the ground is called an action force. The second force is called the reaction force, when the second body applies an opposing force back. In the next section, we'll be looking at levers and how forces are applied in levers. Here's an image representing the three classes or orders of levers. Firstly, a lever is defined as a rigid bar that rotates around a fixed point or a fulcrum. In the first order lever, the fulcrum lies between the force and the resistance, in a seesaw. In the second order lever, the resistance lies between the fulcrum and the force. This lever is helpful for lifting a load, as less force is needed at the end to raise a load closer to the fulcrum. For example, a crowbar or a wheelbarrow uses this type of lever. The final combination is a third order lever, where the force lies between the fulcrum and the resistance. At first, it appears quite difficult to see any advantage in this. However, this arrangement frequently occurs inside the body, where the muscle insertion lies closer to the joint axis than does the load. The advantage for the muscle is that the distance and velocity of shortening during contraction is smaller. The tissue loading is obviously large. This touches on the point of mechanical advantage, which is the length of a lever can provide help. Mechanical advantage is calculated as the distance of the force arm over the distance of the load arm. If the answer is greater than 1, it will provide a mechanical advantage. For example, in a first order lever, you can see in this image the force arm is equidistant to the load arm, so the mechanical advantage would be equal to 1. This shows a balance and doesn't have any mechanical advantage on either way. However, if the force arm were twice as long as the load arm, then there would be a mechanical advantage. Lastly, let's move on to base of support and center of gravity. Starting with base of support. Base of support is the area beneath an object or person that includes every point of contact that the object or person makes with the supporting surface. So, for example, this desk. The whole desk isn't touching the ground, but it has 2 legs that it stands on. The entire area underneath the desk is considered the base of support. Look at this example of different body positions. You can see that every point of contact, that shaded area beneath the person, is considered the base of support. You can see in the first 2 images, there's a very large base of support where there's a lot of points of contact on the ground, and where all 4 limbs are touching the ground is the most stable. The last 2 images, there's 3 points of contact, 2 feet and a crutch, or the head and the 2 arms. This is a smaller base of support. A smaller base of support is considered less stable. And that gives us insight into why babies maybe crawl before they walk. When they crawl, they have all 4 limbs on the ground, and this creates a large base of support. Whereas when they walk, they only have their 2 feet to try balance on. When somebody is standing, their base of support is just their 2 feet. But when we consider balance, and maybe people that have poor balance, we want to widen their base of support. And that's often why we issue assistive devices, to widen that base of support with a walker or a crutch. Moving on to center of gravity. Center of gravity is the single point at which all parts of an object are equally balanced. Our center of gravity is a moving point and moves as we move. The relationship between center of gravity and base of support allows us to understand balance and stability. When you are standing at rest, your center of gravity is round about your navel area. If you lift your arms and displace some of your mass upward, your center of gravity will move slightly upward. And if you lower yourself and increase your base of support, your center of gravity is much lower. We'll come back to how that influences stability. But moving on, line of gravity is another important concept. Line of gravity is the vertical line that passes through the center of gravity to the ground. If the line of gravity falls within the object's base of support, the object is stable. If the line of gravity falls outside the object's base of support, the object is relatively unstable. You can see this here in this first image. With these rugby players, they're creating a pyramid, so they're widening their base of support, and the person in the middle has very high center of gravity, but the line of gravity is within the base of support, so they're relatively stable. In the example of a ballerina, you can see that she has narrowed her base of support to a very, very small point, but she has trained and learned how to keep her line of gravity within that small base of support to maintain her balance. Now that we understand how this influences stability, how does it influence motion? The line of gravity must go outside the base of support to initiate or continue movement. The further away the line of gravity is from the base of support, the greater the tendency the body has to move in that direction. So for example, in a runner, they are constantly trying to move their center of gravity forward and out of their base of support so that their line of support continues their movement. The further away their line of gravity that they can push out of their base of support, the greater the motion or the speed. So this concludes the introduction to different concepts in human movements. Hopefully your workbook exercises and further reading on the biomechanics of human movement in Chapter 3 will give you more insight into these concepts.